All right, question 16 on this practice test gets into set theory. That's kind of fun. Now we got these two sets, x and y, and a function that maps x to y. A and b are some subsets of x, and c is a subset of b, so therefore also a subset of x. And we're asked which of the following must be true. We have two statements of equality dealing with intersections and unions, and then a statement saying that f of c must be a subset of f of b. Okay, so kind of general strategy. The first one is if you're trying to prove the equality of sets, typically the way you do it is you show containment in one direction and then you show containment in the other direction. So for part one here, these two sets are equal if and only if f of the union of a and b is a subset of f of a union f of b. And this f of a union f of b thing is a subset of f of the union of a and b. All right, so when I see equality, I'm kind of thinking, oh, there's two problems sort of baked in here. I got to show containment in both directions. For that reason, I kind of like statement 3, because for this one, I'm just asked about containment in one direction. So I'd probably start with this one. It's probably going to be the quickest. In case I get stuck later, I've at least narrowed my answers down and I can move on. How can I show that f of c is a subset of f of b? Well, that brings me to my second general strategy. If you want to prove that one set is a subset of another set, what you do is you let x be some arbitrary element in the first of your subsets, and show that that necessarily means that x must be an element of your second subset. So really where these strategies come into play is if you're trying to prove something's true. And you don't have to prove that these statements are true, but if you don't know how to get started, kind of trying to prove that they're true and seeing what happens might be a good way to kind of get you going. So if we look at statement 3 here, that f of c is a subset of f of b, you might be able to just talk yourself into this statement being true. If you went about to try to prove this statement, what you might do is just pick some arbitrary element in f of c, right? Because f of c is the a over here. Instead of calling it x, I'm going to call it y. So y is some arbitrary element in f of c. The reason I'm using the letter y is because the subset c lies in x, so f of c lies in y. So little y might be an element in capital Y. Anyways, y is some element in f of c. What does that mean? Well, what that means is there must be some element in capital C so that f of that element equals y. What I'm saying is there exists an x in C, these are capital C's here, so that f of x equals y. But wait a minute, they tell me right here that C is a subset of B. So anything that's in C is also in B. Right? If it helps to have a picture, B is this big set here, and C is just some subset of it. I'm told that x is in C, so I don't know, maybe it's this element right here. But because C is in B, x must also be in B. Because C is a subset of B, x must also be a member of B. But wait, x is a member of B, then f of x, which is y, is a member of f of b. So what we've shown is that if we assume that y is in f of c, then y must also be in f of b. To prove containment, assume you have an element in the first set and show that it must be an element of the second set. If you're able to do that, you've proved containment. That's exactly what we've done here. This statement right here must be true. If you've taken like an intro to proofs class, maybe you would have scratched out logic more like this as opposed to writing out all these words. Whatever, same thing. If you're not at that stage, you might still be able to answer the question just by kind of drawing pictures. All right, here's capital X and here's capital Y. Squeeze it in over here, I guess. And I have some function that maps X to Y. Well, think about where it takes this set B. I don't know what the image of B looks like. Oh, sure, something like that. But if you sort of think about what it would mean for this statement to be false, if f of c were not a subset of f of b, what that would mean is that the image of C is not contained within the image of B. So I don't know, this little C right here, maybe that gets mapped to some set like this, right? B gets mapped to the purple, C gets mapped to the green. Is that possible? Because if it is, then this is a false statement, right? F of C is not contained in F of B. I have parts of C that are not within this purple circle. Well, no, that's not possible because the image of B, the thing in purple, contains the image of all of the elements within B. So the fact that all of the elements in C are also elements in B means the image of all of the elements in C must fall within the image of all elements mapped in B. This can't possibly happen because if this subset C maps down here in the green, then the green is part of the image of B. Purple was drawn incorrectly. I don't know, maybe that makes sense. Since C is a subset of B, F of C must be a subset of F of B. That's always true. So let's see, how much are we able to narrow down our answers? We know that it's not none. We know that it's not 1 and 2 only. I guess that doesn't help a whole lot. We've eliminated 2 of the 5 options. We still got 3 of them left. which statement should we look at next? I guess it doesn't really matter, right? If 1 ends up being false, we know B is the answer, but if 1's true, we still don't know what our answer is for sure. Whereas if 2 ends up being false, we don't know what our answer is. It's either B or D, but if 2 ends up being true, then our answer is E. So it really doesn't matter which of these statements you look at next. If this were like a math homework assignment, what you'd probably do is employ this first strategy to both 1 and 2. Try to show containment in this direction, then try to show containment in this direction. If you can do both, that means that this is equal to this. Then do the same thing down here. Problem is that's going to take you a long time. I wonder if we can get kind of clever and talk our way through one or both of these. So generally in problems like this, what's going to happen are these statements will be true if your function is a special type, like 1-to-1 or onto, but it won't be true generally. So what can help is to narrow things down by considering a function that's not, 1-to-1 or onto. And you can define that function explicitly if you want, like, f equals x squared. So what, -2 would map to +4, but +2 would also map to +4. And 3 would map to 9. Or you can do things more abstractly, like, x1, x2, and x3 map to y1, and y2 respectively. Either way, whatever's easier for you. Anyways, think if I let set A be equal to the set containing the elements -2 and +3. Then set B is the set containing the elements +2 and +3. If we consider A intersect B, all right, we look for all the elements that are in both of these sets, we'd only have the element 3. But if we look at f of A, we get the elements, 4 and 9. And if we look at f of B, we also get the elements 4 and 9. So the intersection of f of A and f of B contains the elements 4 and 9. But if you compare that with this over here, f of this intersection, well, that would just be f of 3. That would only contain the element 9. Clearly, they're not equal. What went wrong? This function wasn't 1-to-1. So that allowed me to take two different elements and exclude the image of those elements by just making sure that those elements weren't in the intersection of the sets. All right, I kind of got rid of the image of -2 and 2 because I looked at the intersection before applying the function. But over here, I apply the function first, and since -2 and 2 get mapped to the same number 4, when I wait to consider the intersection, I don't lose the image of that element. I don't know if these are things that you want to memorize, but generally speaking, the image of the intersection is going to be a subset of the intersection of the images. We're only going to get equality if our function is 1-to-1. So let's see, does that give us enough information to answer the question? Unfortunately, I don't think it does. We already know that statement 3 is true, and we just figured out that statement 2 is false, so this ain't the answer. But I think we still have to evaluate the validity of statement 1, unfortunately. Well, let's see what happens if we try to prove equality by showing containment in both directions. So we want to show that the image of the union is equal to the union of the images of these sets A and B. Well, maybe we can do something like what we did up here. Let's let Y be a member of the image of the unions. What does that tell us? It tells us there's an X in the union, so that f of X is equal to Y. So think about what that tells us. X is in the union of A and B. That means either X is in A or X is in B, or it's in both. Well, think about what that implies. If X is in A, then f of X must be a member of f of A. Or similarly, if X is in B, then f of X must be a member of f of B. Either way, what we have is that f of X, aka Y, is a member of the union of f of A and f of B. If X is over on this side, then f of X is in f of A, but f of X is just Y, and if Y is in f of A, then Y is in the union of f of A and whatever the hell you want. Same logic if we instead assume that X is in B. It looks like we've shown containment in this direction. What about containment in the other direction? Well, we can kind of just reverse our steps. Suppose that Y is a member of the union of f of A and f of B. What that tells us is that either Y is in f of A or Y is in f of B. Doesn't matter which one. Without loss of generality, we'll assume that Y is in f of A. What does that mean? It means there exists an X inside A so that f of X is equal to Y. But wait a minute, if X is a member of A, then X is certainly a member of A union whatever the hell I want. And if X is a member of A union whatever the hell I want, then f of X is a member of f of A union B. What I'm saying is we get containment in this direction just by kind of redoing the proof in reverse. The equality of the image of the intersection and the intersection of the images only holds if your function is 1-to-1, but the equality of the image of the unions and the union of the images always holds. The logic in blue tells us that this statement's true. That tells us that D is the correct answer. Are these statements worth memorizing? I mean, I don't know. If you can memorize it, it'd make this problem really, really easy. But if you sort of just understand intuitively how intersections allow you to kind of get rid of, loosely speaking, points, whereas unions don't allow you to do that same thing, maybe you can sort of understand the argument so that you don't accidentally memorize slightly incorrect statements that lead to the wrong answer. I don't know.